All right. Good morning, everyone. My name is not Louis Akinpora. My name is Aaron Timmons. I'm the Math Content Director for Advanced Kentucky. We are going to get rolling here with our AP Computer Science A Content Review session. Sorry for the technical difficulties. Today, we are joined by Richard Kick, and he will be talking about inheritance, recursion, and general exam prep. So before we get started here, we're going to quickly go through a couple disclaimers. So AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this product. We are intending this for a Kentucky audience, but if there are others here, we welcome you. We will do everything we can to make this as engaging as possible. Contact information for Advanced Kentucky as well as myself is there. Please feel free to reach out with any questions. During today's meeting, we ask that you keep your cameras and microphones off. Please utilize the chat, and then we will make sure all questions get addressed. And then finally, a recording of today's session will be at bit.ly/advky, along with videos of all past review sessions with Mel Hoffert as well as Rob Schultz. So thank you. Rich, I'm going to turn things over to you and take it away.
Thank you, Aaron, and welcome, Renee, and welcome, Caitlin. Hi, Caitlin, are you able to hear me?
Yes, I can hear you.
Excellent. So we are going to be talking about inheritance and recursion. And this first slide that I'm going to bring up after I share my screen is going to be let's see if I present. This first slide will actually have the URL that I believe Aaron made available. Aaron, do they actually have this URL?
They do. If they go to the bit.ly/ if they go to that bit.ly site, there's a link where they can get that. But I'll go ahead and put it in the chat, or you can too, Rich, either one.
Yeah, I was going to actually grab that and put it in the chat as well. And the second link is actually to a zip file with the code that any code I show, any code that I run, you will be able to get that code. So just in case we have any problems, I'll go ahead and copy this and I'll go to the chat window and I'll paste it in. So there's the first URL and here comes the second. And if you guys would go to the icons and give me a green check mark if you actually have access to those URLs. Give me a red X if you could get access to it. And if you have no idea what I'm talking about with those icons, let me know and I will try to help you out. It looks like we may not have access to the little green check marks and red X's. Is that true, Renee? Are you able to put any kind of icons up on yours?
No, the only thing I could put up is reactions. So I could do like thumbs up, heart, laughing emoji, celebration.
We'll use thumbs up then. If you can give me a thumbs up that you actually get access to, yeah, fantastic. Thank you. And Caitlin, did you also get access to the URLs in the chat window?
I need to go onto the link from another device.
So you're not able to see the chat window?
Oh, no, I can. I just...
Okay. So hopefully we all now can see the slides. We have the chat window. Some reason I'm into annotations. I'll get out of that. I'm going to go back to present. And I'm going to begin by talking about, and if I can somehow get rid of that annotation, that would be helpful. And annotation is going to stay there the whole time, is it not? Disable annotations, clear annotations. I've never had the annotations up on my presentation. So does anybody know how I can clear out this little mark that I put here?
Did you click on view options at the top of your screen, maybe? There's annotate, but I don't know if there's the clear works or not.
The only thing I see is disable annotations for others.
Let me see if I
If I go to my Zoom meeting,
can clear all drawing. There you go.
okay. So back to my slides and good, we're ready to go. So I am Rich Kick. I'm from Newbury Park High School in Newbury Park, California. It's about halfway between LA and Santa Barbara. And I am teaching both AP CSA and AP CSP. Could you, Renee, give me a little intro to what you're teaching and how long and what actually maybe you're looking for today?
I have been teaching, hold on, CSA for 3 years. This is my 3rd year, and I taught BC for 16 years. I am here just to learn, and I was hoping more of my students would be here, but I knew there was tons of conflicts with other things. So, but I'm just here to learn and hopefully find better ways to explain things.
Excellent. Thanks, Renee. And Caitlin, how about you?
Oh, I was hoping to learn more about recursion.
Fantastic. And how do you feel confidence-wise with your inheritance work?
So. I haven't gotten that much into it.
Okay. Well, hopefully after today, you'll have an improved confidence. You'll have some more examples and you'll have a better focus on what your students are going to actually need to do to be successful on the exam. So let's continue. And as I was told, we are going to have a little break between inheritance and recursion. So I assume that would come about 8 o'clock my time, which should be about 11 o'clock your time. That's correct, Aaron? Thank you. So the first thing I want to do is put up this slide that is straight from the APCSA College Board course and exam description. And this just kind of reminds us what our students need to know to be successful on any potential question that the College Board could ask and may. And so we have to understand that this inheritance process, this building of classes from other classes, is going to require students to know that there are superclasses and subclasses. We know that in object-oriented programming, terminology is so important. The wording is important. So it's good to make sure your students are not only familiar with the terminology, but specifically which terms the College Board will use on their exams. So superclasses and subclasses, the class from which you're inheriting, and then the superclass, the class that you inherit from. The subclass is the class that you actually created from another class. And then they'll have to understand about writing constructors, and we'll use the word super and discuss how that is used appropriately. Overriding, there are 2 terms that students confuse often, overriding and overloading. We will hopefully emphasize that difference and make sure students understand those differences as well. The use of super to not only call constructors from classes from which we inherit, but also to use super to call methods. We're going to talk about creating references using, we have multiple classes and there is an inheritance relationship. We'll talk about how references will be used to produce kind of results we would like. Polymorphism is a term that I think most students find confusing, especially in their initial introduction. So we will try to clarify what that means and how potentially questions may be asked about polymorphism. And then superclasses, the object superclass, which is the superclass for all classes that we write. In Java, implicitly, it automatically inherits from objects. So we'll have to talk about those methods that you will typically override in order to define the functionality you would like for your new classes. Any questions about any of those particular enduring understandings that we just summarized? Give me a thumbs up if you're ready to move on. Otherwise, just go ahead and ask the question. Excellent. Very nice. So here we go. So if I were to build a class, similar to if I were going to build a house, I would have to lay a foundation, the frame, the plumbing, electrical, all the things that need to go into building a house, I would have to do from scratch. And if I wanted to upgrade, I could build a brand new house. I could lay down a brand new foundation, put in a new frame. It's just so much work that it may not be necessary if all I wanted to do is improve the house a little bit. So instead of saying, let's build a class house and put in all the fields, meaning instance variables, static variables, write the constructors and all the methods, and then build a second class, which would have its own fields, constructors, and methods, we have this ability to actually create a new class from the existing class. And the key word that allows us to do that is extends. And what we need to emphasize to students is when you're building a class that extends another class, the new class automatically has all the things the previous class had, and the new class automatically can do all the things the previous class can do. So now all you need to do to add to this new class is add any instance variables that are different from the original, and any methods that are new, or any methods you would like to rewrite or override. So it allows you to write a new class using much less code. So I need to also emphasize to students that there are two relationships that often describe the relationships between classes. One is A and one is has A. Give me a thumbs up if you've seen those before, or just give me a no if that's brand new. And so what I would often do is ask my students, can you give me an example of two concepts where is another, two concepts where one has another? And by concepts, I'm talking about classes. I often refer to classes as concept models. They actually summarize a concept. So if you would, I'm going to start with you, Renee, since we've already had quite a bit of chat. Do you have a couple of concepts that you think might give a good example of one being an example of it has another, or it is another? And I usually ask my students to give me things they're most interested in.
Well, I'm not interested. Well, I'm a math teacher, so a rectangle, well, a square is a rectangle.
Very nicely done. And you're right. Teachers will give us all the academics. Students usually wouldn't give those examples, but that's a nice one. Caitlin, do you have an example of two concepts? Oh, go ahead.
I was going to say a cat is an animal.
A cat is an animal. Very nicely done. Caitlin, do you have a couple from your areas of interest?
A rose is a flower.
Very nicely done. So those are good examples of is a. Now, has a tends to be a little trickier sometimes for students. So if either of you have an example where you have one concept has another. Maybe even stick with the cat example, Renee, and Caitlin, maybe even stick with the flower example.
A cat has a tail.
Very nicely done. So if you had concept models or classes for those two concepts, you would not say a cat is a tail. You certainly wouldn't say a tail is a cat, but now you have this has a relationship where one would have an instance of another within it. How about your example, Caitlin?
A rose has petals. Or
Very
has a
nicely
petal.
done. Very nicely done. So obviously teachers have gone through and thought this through. Students may need much more time to kind of explore and list possibilities for is a and has a relationship so that they can clarify that. But now when I go to the next slide, we're going to look at a particular class that, again, all students should be familiar with. And this is very confusing because throughout your course, you've probably used the term object quite a bit, but usually refer to it using lowercase o. So you talk about objects that are created from classes. But you have to emphasize there is a large capital O class object, and that class actually has fields and methods. And the two methods that you need to familiarize your students with are the equals method and the toString method. So they need to understand that every class you build in Java is implicitly inheriting from object, and they automatically have the methods equals and toString defined for them. So when you define a method toString in your own class that you're building, what you're doing is overriding or redefining that particular method. And so those are the concepts related to the object class that students should know. And again, it's on page 150 of the course and exam description. By the way, as I go through these at any time, if you have any question, just give me a thumbs up or any kind of action, and I would be glad to address specific questions, because certainly we can customize this as you would like. So the next image is an image that I think students should be familiar with in order to visualize the relationships we just mentioned. Have either of you seen images like this before? Give me a thumbs up if it's familiar. Okay, so this is, oh, there we go. Renee, you've seen it. Yep, both of you have seen it. So Renee, when you see an arrow going from one class to the other, and these rounded rectangles are actually visualizations of classes, what would you say the relationship between classic rock and song is?
Classic rock is a subclass of song. So classic rock is a song.
Very nicely done. Caitlin, what's the relationship between electro song and song?
Electro song is a song.
Very nice. And these look similar, but they're a different relationship. Do either of you have an understanding of the relationship between song tester and song?
I think that would be the runner class.
It is definitely the runner, otherwise known as the public static void main
Yes.
class. Yes. And this little arrow in this particular environment, which is called BlueJ, illustrates that the song tester class has a instance of song, meaning the dotted arrow with the little small arrowhead on it is a has a relationship. The solid triangle arrow is the is a relationship. So song tester has an instance of song, has an instance of electro song and classic rock song. And so if I look at the actual code, and again, I would not necessarily give this example to my students. What I do is have my students discuss what they are most interested in, and we usually build the examples off of their interest. And this was the latest and greatest example from my discussions this year. Students talked about many different concepts, a lot of social media concepts, a lot of activity concepts, but they focused on song as the commonality among the entire group. They wanted to write classes about songs. So we talked about a song having a title, artist, and a duration or a length. And we certainly said that, yeah, there are many, many more things related to songs. But what we emphasize is when you build classes, you don't write everything the concept has. You simply decide what you want the software to be used for, what is its purpose. And if the only thing I'm going to use this software for is to manage which songs I have access to, which ones I'm interested in, the title, artist, and length were the only things I needed. And so I had a constructor, and the constructor had a default setting for the title, artist, and length. And you're going to see later that in my actual code, I decided that nothing was hard to see. So I put a little underscore here instead, so that when you have a default song, it has an underscore title, underscore artist, and a 0 length. And when I say overloaded, I mean, I'm going to have multiple constructors where it has different parameter lists, so I can create songs in different ways. With no parameters, the default constructor, and with 3 parameters, and this could allow me to construct a song sending a title, artist, and length. Are you familiar with the keyword this? Which leads to my absolute favorite question in all of computer science. What is this? Sounds so vague, but it's a very specific question. So give me a thumbs up if you're familiar with this. Otherwise, just say no if it's new. Excellent. So Renee, can you give me your general summary of what you would tell a student this is?
This allows you to use the same variable name as the global and the local.
Very nice. It's a useful tool to allow you to do exactly what you described. Caitlin, do you have anything to add?
It's what's being changed.
It's allowing you to see that something is being changed or assigned. And the thing I want to emphasize to my students is this is a reference. It's much like all the other references, except this reference is used within a class that you're actually writing to refer to the object that you shall be creating using the class you're writing. It's this self-referential relationship, which is very abstract and it takes students a while. But what you can tell them is if you have instance variables and you have local variables that are parameters, and I like the idea that the name is exactly what I would want to use to describe those things. Some people say these are my title, my artist, my length, and a title, a artist, an artist, a length. I just like to say these are the titles, artist, length, and they use the same identity for the instance variables and the parameters. But now I can say this title, the one that belongs to the instance I will be creating using this code, is going to be assigned the value of the title that is passed in as a parameter. So that's what that code does. It will not be used on the AP exam, but it's very commonly used in Java code. So I simply give you that as an example of something I believe students should be familiar with. And then if you look at the rest of the class, we have your standard getters, giving the public access to those values. And then also a Boolean, checking to see if it's a long song, arbitrarily simply set that if it's greater than 180 seconds, it's a long song. And then you'll notice if you go back to the Tostring method, Tostring method was defined an object. So if I define it again in my class that I'm building, I am overriding the previous definition. But I can still get access to that previous definition by using that super keyword. You can think of this as a reference to the object that you're going to be creating using that current class. And you can think of super as referring to the object built from the class you're inheriting from. If that makes sense, give me a thumbs up. If you have some questions about this or super, just let me know. Excellent. Caitlin, question?
Oh, no.
Okay, so I'm going to move on to the next slide. Here's an example of a classic rock, which extends song. And notice I don't have to put all of those instance variables that song had because I am going to build my classic rock object off of a song object. I will have the functionality provided by that song class. So the only thing I need here for an instance variable is something that the classic rock would have that the typical general song does not. And my students decided a guitar solo was something all classic rock songs have to have. So we had a guitar solo duration in here. And there's my constructor. And this is an important issue that you have to emphasize to your students. You may not build a classic rock object unless you first build the song object. And it has actually been done right here, because in Java, if you don't explicitly call the constructor for the class that you're inheriting from, it will implicitly put in the super open and close parentheses, super open and close parentheses. It would still do exactly the same thing as if I don't put it. It will implicitly call the default constructor. Where you sometimes get into trouble is if you try to create a default constructor in a class and the previous class that you're inheriting from didn't have a default constructor, then your code will not compile. But as long as the original class has a default constructor and you don't call it, it will implicitly call it for you. Give me a thumbs up if that makes sense. Give me a question if you have it.
It only
I
will
think we just lost.
will it
Did
only
we just lose Caitlin?
Yeah, she said she had to leave early and that she was going to watch the recording.
Oh, thank you very much. Renee, do you feel an extra joy or pressure of being the only person here discussing this with me?
Both. I wish there was more
How
students, but
about you feel good knowing that you can now ask anything in any direction and I will customize it to your specific question. So if you have anything that doesn't make sense or you have something you want me to address, please jump in, because I love to customize for the people I'm actually working with, not just what you or what I think you should know. So please jump in
I
at any
understand
time.
that, but I'm really liking learning the terminology, because I think that's what's really hard for me is the correct words, like it's a reference, it's, you know, an instance of a class, those things I've really struggled with. But just for a quick question, it only will call the default constructor. So I could put super open close there if I wanted, it's just not needed. And if there's nothing there, then it calls a default constructor. Otherwise it'll do whatever we told, like in the second one, it called the overloaded constructor and then added the new instance variables.
Very nicely said, and you are using the terminology correctly. And sometimes it's not just whether it's correct, you have to also understand it's which version of the correct terminology will the College Board use on the exam. So I can call this an instance field, but I have noticed on the College Board exams, they are typically going to refer to these as instance variables. So it's not right or wrong, it's making sure we're comfortable with the terminology that will be on the exam. So I hope you don't think that if you use a different term, it's wrong. It's just, there are so many different ways of saying the same thing. It's nice to know what's going to be there for the kids on the exam. So in this particular case, if you don't call a constructor for the class you're inheriting from, it will automatically be invoked. And it will always work unless the class you're inheriting from doesn't have a default constructor, and then it will not compile. But you may, even in this default constructor, call the constructor from the previous class. If I wanted to call super parentheses, quote, quote, comma, 0, I could explicitly do that. But because I didn't, it automatically calls the default constructor. Nice question. And notice I must call the constructor for the class I am inheriting from before I do anything else. So if I have an instance variable for classic rock, I must call super before I try to assign that instance variable its value. And so when I go to the rest of this class, notice define any of those other methods. I simply had to define additional methods that the song didn't have. In that case, get solo length returns the instance variable for the classic rock object. And this is something that I wanted to really emphasize. I can now override toString again. I already in song overrode toString so that it would do more than what the original toString for object does. Now I'm overriding the toString from song. And so I am telling it, I still like all those things that the song class toString method did. So I'm saying super.toString. It's not going back to object, it's going back to the class I'm inheriting from directly. And this means that will be the toString for the song class. Plus it will concatenate to that the words guitar solo length, colon, space, and then it will actually put the number for the guitar solo. So emphasizing to students that overriding methods always refer to the class you directly inherited from. You can't jump back to, you'd have to, in the previous class, call the version of that method from that class that it directly inherited from. So song is overriding toString from object, and the classic rock is overriding toString from song. Thumbs up, Renee, or questions? Okay, excellent. So here's the next one, electro song. And so same kind of thing, a new instance field. My students told me something I did not know. All electro songs have a drop time. When do they drop the beat? It's a certain amount of time into the song. And I guess there's some song that they drop the beat almost at the very end, and they were very excited about that. So here is the constructor. Drop time is 30. Implicitly, it automatically called super for the default constructor. And here it's explicitly calling super for, as you said, that overloaded constructor, and making sure it's using those parameters to initialize the instance fields, and then assigning drop time, this dot drop time, to the parameter value. And that's the end of the class. I only had to define that new method. The other methods are automatically inherited. And again, overriding the toString method. So now I actually go to the, what you call the runner, the class that has the public static void main. And notice I'm going to start by creating an array list. And an array list is going to have song references stored in it. And what I love about this example is all of the examples we just talked about, classic rock, electro song, and then the just default song, all are songs. So if I tell the compiler that I want an array list to store references to song objects, I can store an electro song and a default song and a classic rock song if I would like, all in the same array list, because every one of those references is a song reference. Because as we already talked about with inheritance, when you build a new class, the new class is a previous class. So I have an electro song, a typical default song, a second default song, and then a classic rock song, all in the same array list. And I'm going to go through and I'm going to print them out. I put this in only for a discussion my students were inspired to start. This is not going to be on the AP exam, but it tends to be useful. If I have an array list of song references, the only methods I may call using those references are song methods, not methods defined in subclasses like electro song or classic rock. So if I did want to use this song reference and call something like get guitar solo, I would have to check to see if that reference truly is an instance of a special song called classic rock. So if S instance of classic rock, I then can call get solo length. If I tell the compiler specifically, yes, it's a song reference, But because it is an instance of a special song called classic rock, I can cast that reference to a classic rock and then call other methods. Again, this is not testable on the AP, but it tends to be very useful for students doing things with inheritance hierarchies where they may eventually want to call a method that's not a part of just the general song. But the important thing that they do have to know for the exam is down here, if I do print this out, anytime you say system out print or println a reference to an object, it will implicitly call the toString method. So if I put fav.toString, it would do the same thing as if I just say print fav. The same for second. If I put second.toString, it would be doing exactly the same thing. And then very importantly, playlist is a reference to an array list of references. So when I say println playlist, it's actually going to call the toString method for the array list class. And the toString method for array list starts with a bracket, and then it simply displays the result of calling the toString for every reference stored in the array list object. And therefore, it's going to call toString for fav or for second or for all of the different references that I stored in this playlist. And when you look at the result, you see that here's my first couple of displays, just system out println. But when I println the reference to the array list, it actually printlns the reference to the toString for the first reference. And notice that was my electro song. I simply colorized it to make it a little easier to follow. The computer is not colorizing this. I simply went through and colorized. So you could see this is the result of println or printing the very first reference. It was a electro song, and it does the toString from song, plus it did the toString for the super for song, which was the object class toString, which is always defined to do the name of the class, an @ sign, and then the reference, otherwise known as the memory location at which the object is stored. Then I concatenated to that the actual words drop time with the call to get drop time. And that all was my toString for the electro song. Then it went to generic song. So it did the title, artist, and length. And again, I put in the underscores so you wouldn't have to just see nothing here. And it then did call the toString to object. So it still did the name of the class, the @ and the memory location. Here's another song, title, artist, and the toString from object. And then finally, this was the classic rock. And the classic rock called the toString, did the toString from object, and added the guitar solo to it. So what's important is, even though every one of these references was a reference to a song object, they were really special songs. Like this one was a classic rock song. This one was electro song. So at runtime, Java knows to look at those references, and if a method has been overridden, it will call the appropriate version of that method for the specific reference that you have. That ability at runtime to determine which version of the method should be used for that appropriate reference is called polymorphism. And that is an incredibly complex topic that I think if you use toString, you can at least effectively introduce to your students by saying every version of the song had its own toString. The song, the classic rock, and the electro all had their own version of toString. When you call toString, instead of just doing the basic definition from song, it will look to see what type of song it is, and at runtime determine the appropriate version of it if that method has been overridden. Renee, does that make sense, or do you have some questions about polymorphism?
Okay, so I understand that you can create the song and you can print the song and it will know which one to print by the polymorphism. I do not understand why you're still getting the memory addresses. Like I thought, why would it go back to the object
So that's a
toString?
great question. That's a great question. So I'm going to go all the way back to song. There's my, oops, that's classic rock. I'm going to go all the way back to song. And notice I define some variables and I have some constructors. And notice the way I defined toString was title, artist, length.
So if I didn't have
Exactly.
this super dot
Honestly,
toString there, it would not do that memory address.
exactly. And
Okay.
honestly, Renee, I did this months ago. And I looked at that and I thought, wait a minute, why am I still getting the name of that class? And I had forgotten that I put the super.toString, so I had to go back and remind myself. That's the only reason that you're seeing that name of the class @ in a memory location. Remove that, it would simply say the words title, artist, and length. That's a great question. And as I was doing my classroom, Renee, when someone comes up with that level of detail, I really make a big deal out of saying, you have followed the logic that perfectly, because for you to mention that, it requires you to really understand it well. So kudos to you.
Now, just so I can get things straight in my head, this is for an array list. If I try to do this with an array, it would not work because there's not a toString method in the array class, just the array list class, which we import.
Beautiful.
So that would just print the memory address.
And that is exactly what I emphasize to my students. There is a class, but it's not defined in the typical way. It is built within the Java language. There is a class for array, and the array class does not have an overridden toString. And that is why the array class, when you system out print a reference to an array, will simply give you the name of that class, which is in kind of this pseudo primitive like syntax where it has a bracket and then it has a symbol for I for int or D for double. It uses that as the name of the class. It does the @ and then the memory location, because the array class does not have a overridden toString, whereas array list, built much later, actually created as part of a library for Java after the Java language was created, that did have a toString defined, and it's much nicer to use.
Okay, can I ask one more question about arrays?
You can ask all the questions you want. Go.
So we were recently doing the FRQ, which I'm guessing this was kind of maybe modeled, well, not wasn't modeled after, but it had the Hey Jude song in there where it was a list, but on the AP test, it didn't say array list. What's different?
So that is a great question, and one of my favorite topics to teach, but I will warn you to tell your students, list is not going to be testable this year. List is no longer going to be on the AP curriculum, not because it's not important, but because the Java language has changed so dramatically that a lot of the questions I used to ask about list or interfaces are no longer the same answer, because the Java language has redefined and expanded the capability of interface well beyond what it used to be able to do. So interface simply used to be a purely abstract class. It was a class where you only had method declarations and no definitions. And people would think, wow, that doesn't sound very useful. But when you try to define a type in terms of both fields and methods, variables and functionality, you'll find that many types have functionality that remains the same over decades, but instance variables that dramatically change. My favorite example is a car. You have an engine, you have a gas tank, you have an accelerator, you have spark plugs. Now you have a car with no gas, no tank, no spark plugs. All of the instance variables have dramatically changed, yet it still drives, it turns, it stops. So we can define classes in terms of strictly functionality and then use those types to write software that lasts for decades. But if we define types to always be both the fields and the methods, we limit the usefulness long-term for those classes. So because interfaces are so powerful, they were tested, but now Java has allowed professionals to actually define some of the methods, not define others. They have become very, very much more powerful for professionals and incredibly confusing for new students, for intro students. So just tell your students, list is an interface, and array list is a class that implements list, and that will no longer be tested because the test questions would become incredibly complex.
Okay, that's what I kind of told them. I said, just think of the list. In our case, it's just an array list. It's going to do, you're going to add, remove, get, all that kind of stuff. Otherwise, just ignore that it says list in your mind, do array list. Now, is there anybody that has rewritten the old AP problems with interfaces and stuff? Because there's some really good problems out there that I just don't know.
I can tell you my quick fix is I just tell students every time you see the word list, simply replace it with array list, and you can do many of those same problems.
Now, same thing with the interfaces, because there's some good ones out there. And I just kind of tell them, think of it as just a class. It's slightly different, but for us, just think of it as another class that was inheriting something.
Do you remember range and number range?
I don't remember that.
Was and then there was one about sandwich and trio. All of those classes or all of those interface problems, I simply say, here's a class, and I actually define the methods and I actually put in some instance variables. You're exactly right. Every one of those interface questions you can change into simple class questions, and they're still very powerful questions. I still really enjoy them. Great questions, and you're making my morning. This discussion is very enjoyable for me, and we picked up Jacob. Jacob, how are you? I think Jacob's still muted, and so hopefully Jacob can. What's that?
He typed good. His mic is broke, it said.
Oh, excellent. Yeah, I should check my chat window without stopping my sharing. Yep, good, got it. Thank you, Jacob. I appreciate it. And thank you for Renee for giving me the heads up. So I'll go back to sharing. If I can go back to finding my correct window, there it is. So now we're back to this, and I just had some sample questions that I was going to discuss. Now, technically, I guess in a minute was supposed to be our break. Aaron, do you think I should just run over a little bit, or?
Yeah, I mean, we started late, so you can do whatever you'd like. If you want to go a few minutes, that's fine.
Yeah, I'm going to probably go a little 5 minutes longer, and then we'll do our break, and then we can do recursion.
Yeah, no problem.
So here's an example from what was a publicly available question provided by the College Board about bikes and e-bikes. And I thought this was very appropriate because I see bikes around in California all the time. I see electric bikes, e-bikes, and the bike typically has 2 wheels, and they're just going to simply say this class allows you to get the number of wheels. And then an e-bike is a bike. It extends bike. It has 2 wheels as well, but it also has a number of watts, and then you can get the number of watts. So that was their example of a question that could show inheritance in a relatively simplistic example and still be valuable for answering some or asking some pretty sophisticated questions. So the question they created was, if I make a bike object, this is definitely a bike object, but it's a special bike object called an e-bike. So this is an instance of an e-bike, but I'm going to store the reference as the memory location for a bike. And so you're promising to the compiler that this will be a bike reference, and you're using an e-bike object to generate that reference. And that is completely legal. But you have to emphasize to your students that you're guaranteeing to the compiler that you will only use this B reference as a bike reference, which means you can only call methods from the bike class. If you have a method that's only in special bikes called e-bikes, the compiler will tell you, you cannot do this. You promised me you're going to use this reference as a bike reference. Even if you create an e-bike object, you can still only call bike methods. If that makes sense, give me a thumbs up. Questions, feel free to ask.
Picked up one more or two, Rich.
I pick up two more. Hey, Vinesh. If Vinesh can hear me, maybe type something in the chat so I can verify that you actually are here. Looks like he's a blue hornet.
I'm here.
Excellent, fantastic. And after the break, we'll kind of reacquaint everybody and make sure everybody knows who everyone is and try to refocus where we're going to be going. So I emphasize B is a bike reference. That's a special bike. It has all kinds of special functionality like get watts, but I can only use it for this. So when it says system out print B not get number watts and B not get number wheels, even if it's an e-bike and it theoretically could do this, the compiler says, no, no, you can only do bike stuff. So which of the following explains why it does not compile? There it is. You can't call an e-bike method if you promise the compiler you're only going to use it as a bike reference. And so there's the answer. And I believe, yeah, I had one more. Here's an apple class. Here's a Granny Smith, which is an apple. Here's a Jenna Gold, which I have no idea what that is, but it extends an apple. Emphasizing that this defines a method called print color. This overrides the method defined in the original class. And therefore, if you do have a reference to a Granny Smith, it will use its own version of print color. But if you have a Jenna Gold, which extends apple and did not override it, it will go back and use that original definition. So apples will print red. Jenna Gold will print red because there is no overriding taking place, and only the Granny Smith will override and print green. And so now the question was, when will the print statement actually display red? When some apple is an object of type apple, yeah, that's true. When it's Granny Smith, no, it's going to use the overridden version and use green. When it's a Jenna Gold, yes, because it didn't override and it will go back to whatever apple defined it to be. So the answer was 1 and 3 only. So those were my examples of questions. There are many, many more examples that I certainly recommend you go and look through in the CED. I always tell my students I could show you URLs, but please just type APCSA space CED. It will almost always be the first link in your search, and you can get to it that way. And you can search through the entire list of inheritance. You can go back and look at those knowledge statements, essential knowledge statements that we talked about earlier, and hopefully you will have a pretty good handle on what your students are going to have to do on this exam in May. Any other questions, comments about inheritance at this time? Renee, did you get your questions answered?
Yes, thank you very much.
Thank you very much. Your participation was very, very much appreciated. And Jacob and Vinesh, if you would, let's just take a, what is it, Aaron, 5-minute break?
Yeah, 5 minutes works. Yep.
Let's take a 5-minute break, come back at 8:10 or 11:10 your time. And I will start back with recursion. I will stop sharing. And I will probably temporarily turn off my video so that the dog doesn't run back through the picture or something like that. And I will see you at your time, 11:10.
Sounds good. See you back in a few
Aaron,
minutes.
do you have anything from me, Aaron, that you have for suggestions or any questions, comments?
You know, I wish we had.
This is going to be so much fun. So I go to recursion, if I can find my window again. And so I'm back to recursion. I'm still at Newbury Park High School. And here is the course and exam description summary of the enduring understandings. You need to determine code that would be used to complete code segments. Multiple choice is the only time you're going to see recursion on an AP exam. They give you recursively defined methods, and then they will say, here's something's wrong, or how do you fix it? Or there's missing code, how do you add to it? You have to have students, number one, recognize if a method is recursive by identifying the call to the actual methods that's being defined within that method. And they have to understand that there is this thing called a terminating condition, a Boolean expression that will guarantee that at some time, the method stops calling itself. Otherwise, you get this infinite recursion. So we're going to look at some examples. But this shows that you're going to have to just identify code that's given and see changes that are needed. And then searching and sorting are two specific examples of how you can use recursion effectively. In particular, the binary search and the merge sort. So we're going to look at examples of both of those. Any general questions about recursion before we dive into some examples and discussions? So here is my first problem. I would like to draw that picture. And I would tell my students that to me feels overwhelming. That picture is very complex. It would take a lot of steps, and I just don't know that I have the endurance to do it. So what I can do is encourage students to think optimistically in a recursive fashion. Don't draw the whole thing. Just draw that thing. And by the way, the mathematician Koch created this Koch curve, I believe, centuries ago, and it is a mathematical object, but it is a highly useful computer science concept as well. So the Koch curve is what we're doing. Don't draw the whole curve. Let's just draw that piece first. And students will say, yeah, but that still looks like it's going to be very difficult. I don't think I can have the endurance to draw that whole thing. And I say, okay, that's okay. Just draw this piece. Let's just get the little part of it defined. What we're doing is taking a very large task, but recognizing that the task can be broken into subtasks that are very similar, but they're on a simpler level. And as I get smaller and smaller subtasks, eventually I get down to a task I could do. Draw a segment, rotate and draw a little bump, and then continue the segment. Mathematically, they'll often say that you basically take a segment and divide it in thirds, and the middle third has an extra segment added to it so that you form a little top of a triangle, an equilateral triangle. So each one of these segments are of equal length. So you basically draw the segment, rotate 60 degrees, draw a segment, rotate 120 degrees, draw it back down, rotate 60, and now you have the rest of the segment. That I can draw. And if I can draw that piece, all then I would have to do is rotate 60 degrees and draw that same piece again. And then rotate 120 and draw that same piece again. And then rotate 60 and draw that same piece again. And now I have that piece drawn. But if I can draw that piece, all I would have to do is rotate 60 and draw that piece. And then rotate 120 and draw that piece, and then rotate 60. And now I have that piece drawn. And if I could draw that piece, simply rotate 60, draw it again, rotate 120, and now I have that piece drawn. And once I draw that, I simply rotate 60, draw it again, rotate 120, draw again, and now I have the whole Koch curve. So recursion gives students another way of thinking that allows them to take very often complex problems that have seemingly overwhelmingly numbers of steps required, and allows them to see that there is a smaller case that is very doable. And if they simply call the smaller cases and allow the recursive algorithm to do that task, You can solve complex problems like that simply by looking at those smaller cases and getting to a base case that will actually allow us to complete the task. So there's my intro to recursion and recursive thinking. And here is the code that I would show students that I would not expect them to write yet. It would be something that I would expect them to see as, even though the drawing was incredibly complex, the code is relatively simple. If you have a length that's bigger than 1, break it into thirds. Draw the first one, and then turn 60 degrees and draw the next third, and then turn 120 and draw the next third, and then turn back 60 and draw it, and that will do the piece that I want drawn. But if it's not greater than 1, I actually can do something. I don't call itself. I simply do whatever the system allows me to do to draw segments. So I'm going to draw a segment 5 pixels long. I used to have it smaller, but it got so small it was hard to see. And the size of my segment determines how big it's going to fit on the screen. So I just chose this. I experimented and said, let's go 5 pixels, turn, 5 pixels, turn, 5 pixels. And I drew that little baby piece that you saw in the bottom left-hand corner of my original slides. But if it's bigger than 1, it just keeps dividing what is there in thirds and calling itself so that this incredibly complex task becomes a relatively short piece of code. And just again, for proof of concept, to show that this actually exists, I have the code, which, by the way, that second URL I gave you on the first slide is the zip file for all of this code. If I look at this code and I run, it does actually draw the Koch curve. And just to show that that's true, notice when I created this, I started with 1,200 pixels wide and 800 pixels high screen. And I actually started at a point at 10 to the right and 500 down. So it was towards the bottom of my screen. And I said, I want the depth or the number of cutting in thirds to be 4. If I change that to just 2 and I compile and I run again, notice now I'm just doing 2. I say, draw this, turn, draw this, turn, draw this, turn, draw this. But to draw those, I break those into smaller. If my depth is 2, I get a very relatively simple curve. If I change the depth to 3, I get a little more complicated curve. And finally, if I put it back up to 4 where it was, I can actually draw the curve as you originally saw it, and there it is. And of course, students will say, well, what if I go to 5? What's that going to do? And I say, well, you have to have an amount of real estate that will allow you to see it. If I go to 5, it's simply going to draw off the screen. It keeps going. It goes well to the right. But notice the piece that's to the left still looks the same. So I'm really doing more work, but it's not really displaying. So I kept it at 4. So you could explore that code and play with that code if you would like, but I'm going to go back to my slides. And I am going to go back to present. And so there's my first example that I would not be looking for students to write early. I would be looking for them to look at and understand that large tasks that have similar processes at smaller scales can be thought of as recursive processes. Here's a problem that used to be very familiar to my students, but now fewer and fewer know this because this is kind of an old school game. This was a game that students used to play all the time called Minesweeper. And I remember when you clicked, if there was nothing there, it would look all around it and keep revealing everything that's there until it got to something that did have things that could not be revealed, and it stopped revealing. So that whole process was called flood fill. And I emphasize to students again, we don't write this early, but you can see if I tell it a certain row and certain column is what I want to select, and I verify that that's actually on my board, it's between the minimum and maximum rows and columns, and it hasn't been marked. By marking it means I already looked at it, don't mess with it. Then I simply call flood fill 8 times. These loops do not mean I'm iterating to fill. These loops mean I'm calling flood fill above and to the left. I'm calling flood fill directly above. I'm calling flood fill above and to the right. I'm simply calling flood fill 8 times. I could have simply listed the 8 calls. And those 8 recursive calls will actually not only fill the spot that I'm at, but it will do all the spots around. And as soon as it gets to a spot that's not appropriate, it just does nothing. And that recursive definition, which is relatively compact, can fill an entire board if that board was empty or didn't have special symbols on it. A better example that students could actually see is an example of just integers in a 2-dimensional array. And I just filled it with zeros and then any other non-zero numbers. And if I say, go ahead and fill all the zeros with the number 5, because 5 was larger than any entry, it will fill that 5, but it will look up and above and say, wait a minute, let's fill this one too, but there's nothing there because it's off. So it does nothing here, nothing here, nothing here. Then it looks at this one and says, oh, that one's already marked, or excuse me, that one already has something on it. So I mark it by adding 5. This one has nothing, mark it by adding 5. I do to the one to the right, mark it by adding 5. I go down left, mark it by adding 5, mark by adding 5. This one has a 0, mark it by adding 5. Now that I've done this, I have called flood fill on this one as well. So it's going to do the 3 above, the one to the left, the one to the right, that and that. So it fills. I've also called flood fill on this. So it's going to do all the 8 around it. And it's going to continuously flood fill until all of these 5s are replacing every one of the zeros. And simply by changing that one value from a 0 to a non-zero, now notice it didn't fill these zeros because the flood fill only filled around this number. It never got down to these zeros, and these did not fill. So you can tell students about graphics, which are simply pixels that have certain values that you can check with this recursive algorithm. And if those values have the value that should be filled, it will not only fill it, it will recursively fill all the values around it. And if it gets to an edge where it never finds what it was looking for filling, it will stop filling. And that's called a flood fill algorithm, which again, proof of concept, I have the code that will allow me to actually go to this grid, look at the code that has flood fill, look at the main that simply creates the array and then displays it and then fills it starting at any spot I want. In this case, I started at 0, 3, and then I display it after it's filled. So if I run grid, notice it displays the original and then it displays the fill, which because there was a 3 here, never got down to these. Filling around this 0 never got beyond this edge. And if I simply modify this value to be a 0, now when this 0 is filled, it will also flood fill around it and recursively get all the way down to the bottom. I run it again. And now you can see it did fill all the way to the bottom because that one value had a 0 and that flood fill above it forced the others to also be filled. So I use those two examples as visualizations that help people start to think recursively. But those are not easy problems to start with in terms of students actually generating code. So I'm going to look at some examples where they could generate some code and start thinking recursively. Some of my colleagues that present would at sometimes say, but yeah, you're showing them examples that are not appropriate for recursion. You're showing them examples where you would never write it recursively to solve. And that's a valid point. But if you show students examples that are appropriate for the use of recursion, they're usually complex enough that they have difficulty understanding how to implement the code. So I am a believer in taking processes they're very familiar with, that they could write in other ways, like iteratively, and showing them that if they think about it recursively, they could write recursive algorithms that once they understand will allow them to take then much more complex problems, and because of their understanding of recursion, appropriately implement those difficult problems as recursive algorithms. So again, iteration would be appropriate for taking a number to a power. What is 5 to the 4th? You simply multiply 5 by itself 4 times. But I would encourage students to think about it as a complex problem that could be written in a simpler form. It's really 5 times 5 to the 3rd. And what is 5 to the 3rd? It's really 5 times 5 squared. And what is 5 squared? It's 5 times 5 to the 1st. And what is 5 to the 1st? It's 5 times 5 to the 0. And 5 to the 0 is my base case. I am not going to go to negative exponents. When I get to 5 to the 0, mathematically, it's defined to be 1. And therefore, if I ever get down to that case, I'm going to return 1. And once I return the 1, I can go back up and multiply it by 5 and replace the previous call with the number 5. Then since that was supposed to be multiplied by 5 and I get 25, I can replace that 5 times 5 as 25. The 5 squared becomes 25, and I can go back up to the previous recursive call and replace that with 25. Now I multiply that by 5 and get 125. That is the result of this call. And so I can return that back up to its original call. And 125 times 5, 625. And I get the actual value for the original call. If students can see that this iterative algorithm can also be thought of as a recursive algorithm, then they can write code like this. Take the power of a base to an exponent. If the exponent's 0, return 1. Otherwise, simply take the base and multiply it by the power of the same base to one smaller power, where this is progressing to the terminating condition, the base case. Emphasize to students, if they don't have this if statement and you simply say return base times power base x minus 1, you will infinitely recall or recurse. You will call that recursive method infinitely many times, and the computer will stop you and say, you're out of memory, Stack Overflow error. And many of my students have heard of the website Stack Overflow, and then they get kind of excited that they realize that has a deeper meaning than just some crazy words put together. Stack Overflow is the result of an infinite recursion. So I have them thinking about this, and then we go to another one that again is not a problem that would be appropriately solved by recursion, but it is something that once you learn how to think about it recursively will lead you to the ability to solve much more complex problems using that recursive thinking. So I want to count the number of capital letters in this string. So I look at it and I just say, yes, there's 1, 2, 3, 4, 5, 6, 7. I just returned 7 because I'd simply iterate through and look at each one, check to see if it's capital, add it to a count if it is, skip it if it's not, and that would be a nice solution. But I can think of it as a recursive solution as well. Check the first letter and see if it's capital. And if it is, return 1 plus all of the values associated with the rest of the string. So I could simply count this one and then recursively call my process on the smaller string. And if I count it, in this case I do not, I add 0 plus, and now recursively call on the rest of this string. So I look at this count caps, and I immediately emphasize to students, I know it's recursive because I am calling the method inside the definition of the method. Count caps send me a string. If it's length bigger than 0, I can do something, but if it's not bigger than 0, it has no capital letters. I simply return 0. And now I build the string of just the first letter, the substring from 0 up to, but not including spot 1. And that means the first letter. And this was something I actually had to add after I wrote it, because when I counted, I got 7. It got 8, 9, 10, 11, 12, 13, 14, 15, because space is exactly the same as capital space. So it was counting all my spaces as capital letters as well. So I had to realize if it's not equal to space and the letter to uppercase, which is a very powerful string method, which is not going to be testable. It's not a part of the subset. But I emphasize to students, you should go to the Java documentation and use methods that are appropriate for what you're trying to solve. So letter dot to uppercase, if that equals letter, that means it is an uppercase letter. And so I count it. I return 1 plus all of the characters that I can count for the rest of the string. And my students oftentimes confuse this substring 1 as they think it's just one character. It's really from spot 1 to the end, which means it's the entire string except the first character. It doesn't use the character in spot 0. So I return that one is a capital plus count all the rest of the characters. Otherwise, if it doesn't return, it must not have been a capital. I return 0 plus. And of course, I don't need the 0 plus, but I like to use that to emphasize to students, you're still counting. It's just you counted 0 plus, count all the rest of the caps. And again, if it's not greater than 0 in length, you know it has no caps. So when I ran this code, there it is. It printed out, again, proof of concept. I go to count letter tester and I run it and it has 7. And just to show that it's not a trick, I can say this is, I just added 2 more. So now I believe I should get a total of 9. And so now I have 9. So again, showing students code and showing them that this process, which is very typically and appropriately done iteratively, simply iterate through, look at each character, check to see if it's capital, add it to the count if it is, skip it if it's not, can also be thought of recursively. And the recursion allows you to then do appropriate questions later that are more complex, but in a recursive way. So I go back to my slides. And I see that there are websites, amazing websites that will allow your students to do exactly what I've just shown you to do. Not necessarily appropriate recursion problems, but at an introductory level, there are problems that your students who just learn recursion should be able to successfully complete. So factorial is a pretty common mathematical calculation. You're simply taking the product of consecutive integers, starting from the given integer all the way down to 0. And when you do that product, of course, it could be done iteratively, but recursively makes it a very short, compact definition. Counting up bunny ears. My students have all kinds of difficulty because they say, just tell me how many bunnies there are and multiply by 2. And that's exactly correct. but you can also think of it recursively, and that's what I encourage my students to do. So what I would like to do is go to that site temporarily called Coding Bat and give me a thumbs up if you've actually visited this site before. Give me a just no, verbal, if you've never seen it. So Vinesh, I assume you've not seen this before?
No, I haven't.
And how about you, Jacob?
Jacob put in the chat that he has never heard of it.
Excellent. And Jacob, I just put in the chat the actual URL for the site that I'm on now. So if you guys wanted to click on it and follow it, you could, no problem. So I'm going to ask you guys, this is what I would do in my course as well. I would ask my students to explore and look at the names that you think might sound interesting, and then just pick a name that you think is something you would like to explore, and then put it in the chat window, and we'll just go with whatever comes up that's most popular. And usually if there are 3 different ones chosen, I pick whomever is first. Anything look familiar / enjoyable to explore? Thank you. It is very familiar. It is very commonly done. So I'm going to go to Fibonacci. And I recall, and this is what I do to my students all the time, I say, if I want to discuss it, just you can put some comments down here. I remember Fibonacci starts with a 1, and then a 1, and then a 2, and then a 3, and then a 5. What's the next number?
8.
Because why? How did you get that, Renee?
You always add the 2 previous terms.
That makes sense. So I know Fibonacci is an infinite sequence that allows me to build off of not the previous, but the previous 2. And so if I ask you to give me a Fibonacci number for some n, that means if n was, and again, we'd have to look at whether they're defining this as the 0 spot or the 1 spot. They're saying, oh, they're saying you actually should start with 0. So there's Fibonacci of 0, 0, Fibonacci of 1 is 1, Fibonacci of 2 is 1. And so they're saying, what's Fibonacci of 3? Well, it should be Fibonacci of 2 plus Fibonacci of 1. So in general, if you're thinking recursively, it should say return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And if I do that, I'm pretty confident that I should get an infinite recursion, because Stack Overflow, I never told it to stop. It's going to keep calling itself on smaller and smaller numbers, which means they will go to negatives. So does anybody recall what the terminating condition for the Fibonacci sequence should be? You can either say it or just type it in the chat window.
I think we're going to have kind of 2 terminating sequences, because you're going to call
Okay.
it -1 and n minus 2. So Fibonacci, if n is equal to 0, you're going to return 0.
Nice. And again, if there's only one statement in my if, I don't even need my open and close brace. I'm going to just say return 0.
And you're also going to do an else if n is equal to 1, you'll return 1.
And I emphasize to my students that else if is very good, very useful. But if you return, you don't have to use it. And you'll probably see on the College Board exam questions, when dealing with return, they'll often not use else, because they know if they did return 0, it can't possibly get to this line. But else if would be okay. So if it's 0, return 0. If it's 1, return 1. And now that I have those terminating conditions, my students love green check marks. The only thing better than a green check mark is a green check mark with a gold star. I mean, Nick Parlante, Stanford University, wrote this site, and the kids are motivated It gives them relatively simple problems to start with, but it definitely progresses into more and more complex problems that give them visual feedback, and specifically using unit testing, whether or not a particular case is going to work, to give students insight as to what they may be checking or what they forgot to check. So I love this site. It has been around for a long time, and students, I think, really gain a lot of insight and get a lot of good feedback. So it's very valuable. If you haven't explored it, I strongly suggest you do. And you'll notice there is something called Recursion 2. And Recursion 2 only has 8. I mean, that seems like a really, well, the reason is these are much more complex. And these do typically challenge, especially intro students. So there are fewer of them, but the complexity is much greater. Any questions about coding BAT or what we've talked so far about in terms of recursion? Okay, I'm going to go back to the presentation. There it is. And I'll go back to present. And here is, again, from the CED, or actually from the College Board, publicly available questions that if there are modifications, it's because I tried to fit it onto a slide. Here's a problem specifically associated with a very famous algorithm that's recursively implemented. It's called binary search. And give me a check mark, or green, or a thumbs up, or anything if you're familiar with binary search. No, you need some help, you need some discussion. Give me a yeah, I want to hear it, or any kind of feedback. I'll look at the chat window in case you're typing it there.
Yeah, can you go over it, please?
Excellent. Okay, so if you look at a particular sequence, I'll just come down here and use my little scratch pad that I use often in my course. I'll just say, let's put some numbers together. 2, 3, 5, 7, 8, 9. Notice these are not just randomly selected numbers, they're numbers in order. So if you have numbers that are sorted from smallest to largest, ascending order, I want to know binary search if there is an 8. And so if I search, I'm not sure what happened to my code. And if I search for an 8, what it will do is take the entire list and find the middle. If you'd like, you can start with a power of 8. So if I start off with a 1 here and I throw in another 8. If I start with 8 numbers, it's kind of nice because then you know a middle. But what's interesting is with 8 numbers, 1, 2, 3, 4, 1, 2, 3, 4, the middle is between the 2 numbers. So you may even want to start with odd numbers. It's up to you. I'll just start with this 8. And I emphasize to students that all of these numbers have indices, locations. So I'm going to put those up there. And I'll say that's where the numbers are located. These are the actual values. I'm going to search for 8. This is going to be the lowest possible index. This is going to be the highest possible index. It's going to take the highest and the lowest, add them together, and divide by 2. And this is where your students have to understand integer arithmetic in Java. 7 plus 0 is 7, divided by 2 is 3. Many of your students are going to say 3.5, but emphasize to them that when you do 7 plus 0 divided by 2, it's an int, divided by an int, it is 3. It does not round, it truncates all of the values after the decimal. So you get 3. This is what it's going to now use for what they call the mid. So I'll just call them mid. And now because that's M, it's going to look at that value and say, is that the number you're looking for? No. Well, you get more than just no. You also say, is the number you're looking for larger or smaller? And since you have a since you have a 5, it's smaller than what you're looking for. You guarantee that everything to the left cannot possibly be an 8. You've simply eliminated over half of the list simply by looking at the number in the middle and realizing the number you're looking for is larger than what you found. So you've eliminated half the list. Thus the name binary search, chop in half every search step until you're down to the number you're looking for. Here's the other nice thing. If I know that the value at the middle is too small, I no longer have to look at that. So I can now take the low and I can put it here, which is one beyond what I just looked at, because I know everything here and lower is no longer possible. So now low is spot 4 and high is spot 7. Now I do a 7 plus 4. And so rather than erasing this, I will copy and say, now I'm going to do a 7 plus 4 divided by 2, which is 5. And so now my mid is 5, which is this spot. And I look at that number and I say, even though there are two values of 8, the first one I found was in spot 5, binary search would return the number 5. And that's how binary search works. Vinesh, does that help? Or was it Jacob? Renee, are you good?
Yes.
Renee, do you understand how much I enjoy that feedback?
I know.
Thank you so much. There's nothing more difficult than teaching to a quiet classroom, so I appreciate the interaction. Back to the slides. So here is binary search, and here's how you would implement that. You must send it the reference to the array that's containing the values that must be, by a precondition, in ascending order. There's your left, there's your right, and then they called that X. Sometimes they're calling it target, sometimes they're calling it value. Whatever you have is the variable or the identifier. That is the number you're looking for. As long as the right is bigger than or equal to the left, you have a chance of finding it. But if the right ever becomes smaller than the left, you know that you've gone beyond any possible search. So therefore you simply return -1, the number is not in the list. So there's my terminating condition. As long as the right is bigger than or equal to, it's going to do a recursive call. As soon as the right is smaller than the left, it terminates. Calculates the mid. Is that number what I'm looking for? Return the spot where you found it. Otherwise, if the number is bigger than what you're looking for, reset the binary search so that because the number is too big, nothing larger will work. So make the right shorter by 1 less than what you just looked at. And the only possible case left is if the number is smaller than what you're looking for. Therefore, you need to look bigger, and therefore you update the left to be 1 larger than the last one you looked at. There is a relatively compact but incredibly powerful binary search that they definitely ask questions about on the AP exam. And so here's a particular example. It's just a list of numbers. You do binary search on that array, starting from 0 to the last position in the array. They could get tricky and say, here's a question. What if I change this second index to not be the last? Maybe I'm only going to search on a part of the list. So I would emphasize to your students, make sure they look at these parameters to verify it really starts at the beginning and goes all the way to the end. And that's the number it's looking for. So what is the value of search if nums is 0, 4, 4, 5, 6, 7, and you're searching for the 4? Go ahead and put it in the chat window if you have a good guess. So Renee, you want to talk through how you got it?
Well, when you do the bisection, it's immediately going to pick the 0, 1, 2 position and compare it. And I think it found it.
Because 0 plus, this is the 5 position, is 5 divided by 2 is 2. 0, 1, 2. And because it found it, what will it return?
I believe it returns the position it was at, but I can't remember what the code said.
Which means it returns the 2.
Oh, I'm sorry, 2. I thought
Yeah.
at first I thought iterations, it takes one call. Sorry.
But my students do the same thing. They will type something, but then they will explain it purposely. So I know what you typed was not what you meant. What you typed was, again, thinking of a good answer for another question. And what you explained was perfect for the answer for the other question. I remember having professors where they would ask a question, you'd answer it, and it would be a correct answer, but it wouldn't be for what they were thinking. So they say, oh, that's wrong, that's wrong. So I always emphasize to students, no, it's not what you answered, it's what you're reasoning. Your reasoning was perfect. I totally understand what you did, and both of them are correct. Hey, thanks, Vinesh. I'm glad you were here. I think we lost him already. But here, as you pointed out, Renee, are many, many other types of questions. How many times does binary search get called? You're exactly right. You've answered both questions already. It's 1. And then I would encourage you to try searching for other things, like what is returned if you're searching for 7. And even if they don't know binary search and they know it's just a position 0, 1, 2, 3, 4, 5, it's very likely they could come up with 5 will be returned. But how many times will binary search be called? It should have said binary search, not B search. Then that one could be a little trickier. Notice in the first mid, it's going to be here. And because that number is too small, it's going to make low here, which is 3. High is 5. It'll be 3 plus 5 is 8 divided by is 4 is 1, 2, 3, 0, 1, 2, 3, 4. That's still too. So for the first one, it was too small. For the second one, it's too small. And now low and high will both be 5. 5 plus 5 is 10 divided by 2 is 5. And it does find it. So it was 3 calls to binary search. And now making sure they understand how to do it if you have a number that's not in the list. What will be returned, even without looking at the code, if they understand the algorithm, they should know what is returned as -1. And if you're searching for the 3, it's going to try the 4, know that it's too big, update the high to be 1. So 0 plus 1 is 1 divided by 2 is 0. Now it's going to look at that. When it sees it and it says it's too small, excuse me, it's too large. Oh, it's too small. Excuse me. 0 is too small. It's going to update low to be here. And now both low and high will be at the same spot and it will not find it. So it's the third call, the first, the second, the third. And now when it doesn't find it, it actually makes the left go bigger than the right. And that last call where the right is actually smaller than the left will cause it to return the -1, but they have to understand that extra call has to take place after left and right have crossed. Does that make sense, or do you guys have more questions or comments?
The most amount of calls it could make for not to find it would be 2 to the n, where it's equal to the length of the array.
Yeah, and
Is that
what gets a
correct?
little confusing is that 2 to the n is like building from the power up. Logarithm is kind of going from the number back down. It's usually the log of the number plus 1,
Okay.
unless the number is a power of 2.
Yeah, okay, yeah, it would, yeah,
Yeah,
perfect, thank you.
very nicely done. And again, you could, if you had more time, actually go to your little scratch pad and put the numbers out and go through step by step as I did in the previous example and show students how to trace it and emphasize to them what I did just recently with my students. Once you know the binary search algorithm, you glance at the code and you confirm it's really doing binary search, you can then answer all these questions without looking at the code. You can simply do the binary search algorithm and answer the questions. So that saved them a lot of time. Speaking of time, I don't think we have any other time. It is, in my clock, 8:59, which I believe is 11:59 your time. Aaron, did you have anything else? By the way, I did have the merge sort, so you guys hopefully at your merge sort and see that it is another kind of a binary operation where you split things in half. You take the halves and split those in halves. You take the halves and split those in halves, and then you merge. And merging simply means take the 2 ones and whichever is smallest, put it into a new list, and then copy the others down. When you merge, you're actually doing the sorting process. And it's going to ask you about how many times do you merge, what did the list look like when you actually merged the last time? Those are very common questions. So hopefully you guys can look at those at your leisure, see the code. A lot of great examples on AP Classroom, so you can search through those and share those with your students. But again, I look to Aaron to see if there's anything else we need to do to clear this up.
Nope. I'm going to start sharing my screen. I just got one little closing slide to do. So I'm
Okay,
going to do
you want me
that.
to stop sharing? Oh, you already took it.
We're good there. So again, Rich, yeah, thanks. I know that we had a smaller number of people, but I know that all of them probably found this extremely useful with the CSA exam coming up very soon. So Rich's contact information along with Advanced Kentucky and mine are on the slide there, along with links to a recording for today's session as well as the handouts that we went over. So with that.
That is not my contact information.
Sorry?
That's not my email address.
Oh, sorry. We will get that fixed, Richard. If you just, I'll write it down.
Yeah, it's our kick. I'll just put it in the chat window.
Okay.
It's
right.
our kick at conejousd.org.
Gotcha. Okay. So I will get that updated so that we have accurate information here. But again, Rich, thank you so much. I know you had an early morning to do this for us, but we certainly appreciate it.
But now I have the whole day that remains, so it's a good news. Good news.
Go have yourself a mint julep and watch some horse races.
Excellent.
All right, you take care. Thank you, Renee.
Thank you all. Renee, great talking to you. Thank you, Jacob.
Thank you.
Thanks, Aaron.
All right, thank you so much.
Bye.